Hey everyone, and welcome to this explainer. Today, we are diving deep into NumPy, which is short for numerical Python. Look, if you're just starting your data science journey, you're going to want to pay extremely close attention to this one. This is the absolute bedrock. It's the foundational library powering Pandas, TensorFlow, PyTorch, basically the entire Python data science ecosystem. Honestly, if you've used any of those tools, you've used NumPy, whether you realized it or not.
Okay, so here's our roadmap for today. We're going to hit the Python speed problem, creating arrays, slicing and views, the magic of broadcasting, and finally, aggregation. Let's jump right into the why before we tackle the how.
Section 1, the Python speed problem. To really appreciate NumPy, we first have to understand the massive bottleneck we inevitably run into when we try doing heavy computations in plain old native Python.
It's so common for beginners to ask this perfectly logical question. Why not just use Python lists? Why learn a whole new tool if Python already comes with built-in data structures? Well, Python lists are incredibly flexible, right? You can throw numbers, strings, even other lists all into the exact same bucket. But that extreme flexibility, it comes at a really steep performance cost.
Here's the core trade-off. Every single element in a standard Python list is actually a totally separate Python object scattered somewhere randomly in your computer's memory. The list itself just holds slow pointers to those objects. But NumPy arrays? They store data in a single, lightning-fast, tightly packed block of memory, and every element is the exact same fixed type. Because it's so strictly uniform, NumPy gets to use highly optimized pre-compiled C code under the hood.
And because of that fixed-type architecture, NumPy is typically 10 to 100 times faster than native Python. We aren't talking about a minor little optimization here. That is literally the difference between a script taking a few seconds to run versus locking up your machine for hours, especially when you start processing millions of data points or massive image files.
So, the real game changer is making the mental shift to something called vectorization. This is probably the biggest leap you'll make starting out. Vectorization just means we stop writing explicit for loops in pure Python. Instead, we operate on the entire array all at once. You just let that C code handle the looping for you invisibly, which saves an immense amount of processing time.
Section 2, creating arrays. Let's see how this all builds in to actually spawning these efficient little memory blocks so we can start playing with them.
All right, here are your absolute daily essentials. First, you've got np.array for turning your standard lists into NumPy arrays. Then np.arange, which works exactly like Python's built-in range function, but spits out a fast array. And then there's np.linspace, which is a total lifesaver. Instead of trying to guess a step size, you just tell it exactly how many evenly spaced points you want between two numbers. Knowing these, like using linspace to quickly mock up test data for a plot, will save you so much time.
Now, I know it's super easy to look at the random functions and think, wait, what is the actual difference between rand and randn? The secret is literally just that letter n. Regular rand gives you a uniform, totally flat distribution from 0 to 1, but randn with the n gives you a standard normal or Gaussian distribution. You are going to be using randn constantly when you get into initializing neural network weights later on.
Once you've created an array, you need to understand its anatomy. You can check .shape to see its dimensions, .ndim for the number of axes, .size for the total element count, and .dtype for the data type. Make it a habit to check these, especially dtype, because whether you're storing a 32-bit integer or a 64-bit float matters hugely for your memory usage and mathematical precision.
Moving into section 3, slicing, filtering, and views. Now that we have our arrays, how do we actually grab and filter our data without slowing everything down to a crawl?
Pay close attention to the comma-based indexing syntax here. If you want row 1, column 2 of a matrix, use matrix bracket 1, comma 2. Beginners almost always try to use double brackets, like they would with normal Python lists. And yeah, while both technically work, the single comma syntax is idiomatic NumPy. It accesses the element directly and instantly, instead of inefficiently creating a temporary intermediate array in the background.
And then we have Boolean masking. Guys, this is an absolute superpower for cleaning data. Instead of writing a bulky for loop with some clunky if statement inside, you literally just write your mathematical condition directly against the array itself. NumPy instantly shoots back an array of true and false values in the exact same shape. You then use that mask to just instantly filter out negative values or squash outliers. Boom, it all happens in place, no loops required.
But we do have to talk about a really critical warning here. Slicing a NumPy array does not create a new array. It creates what's called a view. This is amazing for saving memory, but it means if you modify a slice, you are silently modifying your original dataset too. It's like looking through a different window into the exact same room.
So, here's your golden rule to avoid those incredibly frustrating data mutation bugs. If you need an independent array that you can safely mess around with without destroying your original data, you must explicitly call .copy. Seriously, write that down. It'll save you hours of ripping your hair out debugging invisible data changes.
Section 4. The power of broadcasting. We have arrived at the crown jewel of NumPy, and honestly, the most powerful conceptual idea in the entire library.
Broadcasting is this brilliant feature that automatically stretches arrays of different shapes so they can be mathematically combined element by element, but it does it without actually duplicating any of the data in memory. It's totally conceptual stretching. This lets you instantly normalize a massive data set or add a bias vector to a matrix across thousands of rows. You completely dodge those slow loops and your code stays perfectly memory efficient.
Of course, NumPy needs to know how to stretch your data, so there are strict compatibility rules. First, it compares the shapes of the two arrays from right to left. Second, dimensions are compatible if they are exactly equal. And third, they are also compatible if one of them is simply the number 1. If you just follow this clear 3-step checklist, you'll know exactly how NumPy is stretching those invisible memory dimensions to make your math work.
To get your shapes to line up for this broadcasting magic, you're going to rely heavily on reshaping tools. You'll use .reshape constantly to reorganize dimensions. Now, if you need a flat 1D array, .flatten returns a completely new copy, while .ravel returns a faster view. Actually, remember that whole view versus copy danger we just talked about? Yeah, it totally applies here with Ravel, so just know which one you're grabbing.
All right, final stretch, Section 5, aggregation and real-world context. Let's pull back and look at how we summarize all this data and step into the wider machine learning ecosystem. NumPy has fantastic built-in aggregations like sum, mean, standard deviation, you name it. But the axis concept, that trips everyone up. Just remember, axis equals 0 operates down the columns, which effectively collapses the rows. Axis equals 1 operates across the rows, collapsing the columns. When you're using these aggregations, try to visualize it spatially. The axis number you type in is the dimension that gets crushed down and disappears from your final output. Also, you really have to watch your math operators here. A standard asterisk just does simple element-wise multiplication, but the @ symbol, or np .. performs true linear algebra matrix multiplication. Mixing those two up is such a notoriously common bug when you start building neural networks. Drill the difference into your brain now and thank yourself later.
We've covered a ton of ground, so here's a quick reference cheat sheet of the absolute essentials. Snap a screenshot of this if you need to. Because here is the real secret. Once you've mastered this shared vocabulary of arrays, views, broadcasting, and aggregations, you have secretly just learned the underlying mechanics of pandas, OpenCV, PyTorch, and TensorFlow. They literally all borrow heavily from NumPy's playbook.
Which brings us to my final thought, and a bit of a challenge for you. Muscle memory is everything in data science. So can you open up whatever Python code you're working on today, hunt down those explicit for loops, and replace them with a vectorized NumPy operation? Seriously, don't just passively absorb this. Go load up a dataset right now and put these superpowers to work. I guarantee it's going to change the way you write code forever. Thanks for tuning in to this explainer.